Hello and welcome to another webinar where we'll be discussing teaching grade 10 quantitative aspects of chemical change. Phil, I don't know how many times I've been practicing saying that and still it doesn't roll off the tongue.
I don't think it does for many of us teachers either. So, I mean, it's quite a tricky word.
At least you spell it the way you say it.
Quantitative.
Yes, yeah. It's got that many syllables. No letters hiding anywhere or silent or...
Sure, fair enough. Fair enough.
Welcome, Phil.
Thank you so much, Helen.
It's good to have you back. And hello to Dylan, who's behind the scenes, pressing the buttons. Remember, if you want to talk to us, which you should, because you can win airtime if you talk to us.
Absolutely.
Yes, a 110 Rand voucher if you talk to us either on Facebook or Twitter. And that doesn't mean that if you talk to us, you win. You have to be one of the lucky chosen ones.
So you've got to try.
Yes. Hashtag MeScience if you're on Twitter, and then if you're on Facebook, find the Digital Classroom South Africa Facebook page. You'll find the post. Dylan will be watching both, so say hi to Dylan, and he'll pass on any remarks that are particularly interesting, or maybe questions that are as well.
Absolutely. Awesome.
Okay, Phil, tell us a little bit about yourself.
I'm a high school teacher at Redham House in Bedford View, and I've been teaching for 10 years. 8 of those have been matric. I had a background in research chemistry, and I decided I rather enjoyed teaching people rather than doing the research chemistry itself. It was just way more exciting.
It is.
Absolutely. I mean, kids are way more unstable and unpredictable than chemicals. I really, really enjoy the challenge.
Yeah, and trying to think of how to get a concept across to them so that they actually understand it.
Absolutely. That's the challenge.
It is.
Hopefully today we can help out with that.
Yes. Now, Phil, if you wanted to win a phone or a tablet, which unfortunately you can't and neither can I nor Dylan, but if you did and you were watching this show, all you would need to do is watch out for the secret code that will be displayed somewhere at the bottom of the screen at some point during the show. Write it down and then submit a teaching resource to us. We'll then make the resource public, and we'll choose a couple of really, really great ones, and they'll be awarded a great phone or a great tablet.
Absolutely. And this section is great for sharing resources.
Yes, it is.
So, get sharing.
Yes. Now, you've been here for the grade 11 quantitative aspects.
Yes.
And now you're here for the grade 10.
Sure.
What is the difference between the two?
Well, in grade 10, this is where we start laying the foundation for the mole concept. And this is where we start to talk about, how do I measure chemicals? Grade 11 tries to refine that, and it moves on to slightly more complex aspects of it. Things like limiting reagents and using concentration in calculations moves in grade 11. Grade 10 is just all about the foundational concepts, and hopefully we can get rid of some of the confusion there.
Do you have much time to revise these foundational concepts in grade 11?
I find that very often it's time well spent. Especially when you get to grade 11, it's worthwhile quickly recapping the grade 10. I don't think you should ever assume that the kids have gone home and thought about moles for the entire year in between.
But why not?
Look, I mean, I get very excited about moles, and that's the only way that the kids can get involved and excited themselves. But a lot of them are forgotten. I mean, there's equations all over the place. I've drawn some of them out here, and the kids tend not to think about it in the intervening time, and there's not much work which links in with it. That's the one thing that happens. In grade 10, it tends to get taught as a separate concept, and then it gets left alone. And only in grade 11 and 12 do they start picking it up and assuming that you know what you're talking about.
So I suppose if you want them to remember this for a year's time, your lessons should be memorable enough.
Absolutely. There should be a demonstration, a hook that catches them. And
I'm so glad you said a hook, because that's what we've got to talk about now. I don't know if you saw the slide, but we're talking about the hook in the Teach Like a Champion, and Dylan's going to put up the slide now.
Oh, fantastic.
And it's the 12th step in this book, and it says a short introductory moment that captures what's interesting and engaging about the material and puts it out front.
Absolutely.
Yes. Now they list a whole lot of things, and this book was written by a language teacher, so he likes to talk about stories and analogies and things like that.
Sure.
But you can have a lot more fun with chemistry, can't you?
Well, we're privileged as chemistry teachers. We get to blow stuff up and call it work. So, I mean, kids are always asking us, and every science teacher out there knows that every lesson is started with, what can we blow up today? Unfortunately, most lessons don't go that way, but it's important at the beginning of a section just to sort of captivate their imagination, and that's what the hook really is for me. And it's just to pull the kids in and say, well, we're going to do something really cool, and we'll show you some details along the way, and sort of that covert curriculum that you can introduce by just having their fascination.
What do you mean by covert curriculum?
Well, it's kind of like, exercising without knowing that you're exercising, playing a game to exercise.
Okay.
If the kids are having fun, they don't know that they're actually doing hard work.
Okay.
So if you're introducing some sort of concept, they're saying, yes, give us the details so that we can help you do whatever you're doing, because they're excited and interesting.
Okay.
Well, that's the thing. That's the covert learning that I'm talking about. It's project-based learning, and you're saying, okay, well, here's an exercise. And the kids start to talk about it, and they carry the conversation outside the classroom. And that's where a lot of the learning actually happens. They've discussed it at break time, or they've gone home and they've revised it in the car or the bus on the way home. And that's where a lot of the learning that you don't see goes on.
Yes.
Especially in science. I get really excited when I get report backs from parents. My son told me about the science lesson.
Sure, that's fantastic.
So that for me is a sign of success. It's not so much, okay, they got the light bulb moments in class. Yes, that's great. But if a parent said, no, well, my son was talking about this experiment, what was going on?
Yeah.
That for me is a moment of success.
Yeah, I know how few stories you get at home as a parent. So well done if you're getting report backs from parents.
Yeah, well, hopefully we can give some tips today. Some of them have to be done indoor, so we're limited in the scope, and we don't have a big.
Do you mean outdoor?
Well, I'd like to be able to do some demonstrations, and I'm going to give some ideas for once which teachers can use.
Okay.
I'm going to give a list of just really easy experiments to do that really pull kids in.
Okay.
So maybe later on in the show we can drop a few hints and ideas there.
Good. Shall we look at the 3 pressure points that you've set up for us? The first one says, avoid focusing on calculations and answers, spend time on the concept.
Okay. As I said, calculations are very daunting for a lot of the kids, and I feel that too much time is spent in most classrooms on calculations. They are the boring and the dry part of this chemistry. And if teachers start with them by putting up, these 3 equations are very often on the board as you walk into a mole concept. So, I've just drawn them up
and they're
here.
horrible.
Well, especially to a grade 10 learner.
No, but look, there's a capital N and there's a small n.
Sure.
And there's
There's one that says Mr.
There's one that says Mr. So, as I read this is just all letters. Some of them capital, some of them are small. They look almost interchangeable. I've got an equation here which is made up almost purely of n's. So there's n is equal to n over n, and a child looks at this and says, what is this meant to mean to me?
Yes.
And they're not even told the reason why they're learning these equations. They're not told where these equations come from or how they're useful. So for me, it's important to teach the why instead of the how.
Yes.
Why are we learning about these equations? What do these equations actually do for me is the important starting step. Going straight into, here's molecular mass, and all of a sudden you're bombarding the kids with jargon and equations, and they tend to put up a wall.
Yes.
And once that happens, you've lost them. And, that's game over for you as a teacher. You have lost that child. And try and avoid that as possible.
And, of course, teenagers, once they've decided they can't do something.
Absolutely.
That's it.
They are absolutely correct. Once they've decided that, they can't. And there's nothing that you can do to convince them, and it takes a lot of convincing.
Yeah.
Especially for maths and science, those blocks form very, very easily. So bombarding with equations and Avogadro's constant, a no-no, I would say.
We had a maths show. As you know, we have maths shows regularly. But last week, Tuesday, Lee said something along the lines of concept or practice without concept knowledge is practice wasted. Something to the effect of if you're doing something without understanding why you're doing it, that time spent practicing it is wasted.
Look, there are learners that will go along with it. They are very good at following instructions. They're all about underlining in the correct places, making sure that they are correctly filed. They will follow it. They will get you 100%.
Yes.
But they're in the minority, and those are not the kids that are going to understand in an unfamiliar situation. And they will learn by process rather than, truly understanding what you're doing. And this is very often the test case for understanding in chemistry. This is one of the most studied examples of understanding, especially in chemistry. There's a lot of research on how to teach the mole, and there's a lot of argument and debate because it's something which is generally quite poorly understood.
So your way is not necessarily the right way.
No, and I'm still looking for the correct way. And I think all good teachers should be constantly refining, reflecting, and saying, okay, well, that worked. That didn't work. Let me try something different next year.
Okay.
And, luckily we've got kids for 3 years, from grades 10 up until 12. So, they are our living experiments. So hopefully we get it right somewhere along the way.
Well, let's hope so. Yes, Dylan.
So I just wanted to make a comment on the point that you've just made that I thought was really good. That very often as teachers, I think we can almost be paralyzed by looking for the best practice.
Oh, yes.
And I'm not sure that exists in teaching. I think there's good practice.
Sure.
But I think that there are a range of ways in which to tackle a particular concept or a particular section of work. And not to get paralyzed by thinking, well, I'm not going to try anything because I don't know that it's going to be the best. And your comment then after that was how important it is to continue to reflect and refine.
Sure.
And that as teachers, we shouldn't ever stop learning.
Yeah, absolutely. Well, I mean, that is the thing. So hopefully by the end, and you're going to figure this out in little extra lessons after school or a commented break, whether or not the child has got it. And what about your teaching methods have actually stuck? And sometimes I've been very surprised at the things which have actually worked surprisingly well. Like Dylan was saying, you can get that analysis paralysis where you are sort of in your own head trying to figure out the best possible way, and how it comes across is always going to be a different thing. The curriculum as it goes in the classroom is always something slightly different to the plan.
Yes.
So, yeah. I mean, I'm just going to share some of the things that have worked well for me, some of my opinions.
I look forward to them. Shall we go through the last two pressure points? Use a wide variety of examples involving molecules, ions, and even physical objects.
Okay.
Yes.
Now,
I know you've got things to illustrate just now, so I'm going to read the last one and then we can jump into the stuff.
Fantastic.
Okay. And the last one says, strengthen and revise students' ability to represent chemical change.
Okay, now that one's a bit broad, so we'll expand on that as we go.
Okay. Well, let's start with the stuff.
Okay, well, what we're going to call stuff today. The one thing that I noticed, and this was just by trial and error, was that when I was asking kids to represent mole concepts or to calculate numbers of moles of things, I wasn't giving them a wide enough variety of examples. And I tended to stick to very sort of conventional examples of here's a formula or here's an element, calculate the number of moles of. And the one thing that struck me was they arrived in an exam and the exam asked them to calculate the number of atoms inside a molecule or the moles which were present of a particular ion in solution. And they were completely bowled over because according to them, their teacher had told them that moles is a number of particles, which is usually molecules or atoms, and that's how you calculate moles. Now, this exam was asking them, questions about ions and atoms within molecules, and they really need to be equipped with as many different viewpoints on the mole.
Okay.
Now, if they don't get the concept, obviously, then they're not going to be able to apply it in a new situation.
Yes.
So part of the stuff that I like to do is I like to show kids a variety of single moles of a particular substance.
Okay.
And I've brought in a couple of examples. I mean, this is just very, very easy to do with kids with a simple balance. You can use a triple beam balance or a mass balance, and you can just ask kids open-ended questions.
Now, just to confirm, a mole is a number of particles.
Absolutely.
Okay, so like 100 centimeters represents a meter. A mole represents a certain number.
Correct.
Okay.
It's symbolic. So usually how I start the lesson, I actually don't tell them immediately what the mole is. I'd like them to sort of discover that the mole represents something, but we're going to try and figure out.
Okay.
And it sort of creates a curiosity, which I particularly like. I've chosen very, very different examples of things, and I've told them that I have 1 mole of each one of these substances. I'm going to measure out 1 mole.
Okay.
So they know that a mole is some sort of way of measuring chemicals. But then I sort of throw out a lot of their conceptions about how much of something I have. Because I put the masses to show them that it's not the mass which is linking these things. I show them that a mole has nothing to do with the color of the chemical. I've got vastly different volumes of chemicals as well. So I'm trying to get rid of some of the conceptions that they have about measuring things. So do I have a cup of something, or do I have some grams of something? No, those are not the way that I can measure a mole. So they start to question.
Yes.
And they start to say, well, what's similar between these completely dissimilar things? I've got a metal over here, I've got an element, I've got a compound over here, I've got another, and this is now a non-metal and a metal, so that can't be the commonality between them. So creating that little bit of intentional uncertainty,
Okay.
I try to start to link these up with each other. And they say, okay, well, there's something in common with all of these. There's the same number of particles inside all of these. And then they go, okay, well, how many is that? And then you can be led into the question, well, how much is a mole? How many atoms do I have in 2 tablespoons of aluminium, for instance?
Okay.
So that's where I start to introduce Avogadro's number, and I say, okay, well, that's a lot of atoms. And leading from these, I really do encourage teachers to start giving real-life examples by saying, how big is a mole? If I calculated a mole of marbles or a moles of grains of sand, how big would that be?
So I have a question.
Yes.
Is the term measuring the correct term to use when talking about the mole?
Not as such. The way that I use measuring is because it's what kids have grown up with in terms of counting out something,
Okay.
quantifying. And, that's where quantitative comes from.
Yeah.
So how do I quantitatively analyze something? But that's a really sort of wordy way of saying things.
Yeah.
So I like to say that I can measure out a mole, but how would I do that? Now, it's apparent from these that I can't do it directly by mass.
Yes.
So
Nor
I tell
by
them,
volume.
well, absolutely. Nor by color or by element or by compound. So these are none of the things that tell me. So it disconnects the mole from any one physical attribute, which I particularly like. It sort of disarms them, because very often learners have got crutches. They say, okay, well, that's how I'm going to do this. Or they like to link it to something familiar. Oh, a mole is talking about a gray substance in a beaker.
Yes.
No, it's not. It might be yellow or clear or white. A mole is talking about 1 cup. No, it's not. So it just kind of disconnected from all the old concepts that kids have got about chemicals. Because they've got a lot of preconceived ideas about what a chemical is and how to measure it.
Yes.
And that introduces the necessary. How do we know how many particles have actually got inside this?
Could you say that you're counting out a mole?
Absolutely. You can count out a mole, and that introduces it as a number, which is actually a much more correct way of saying it.
Okay. I wonder how long it would take you to count to...
To count out a mole? Well, I presume it would take hundreds of lifetimes. I mean, we're talking about 6 with 23 zeros. Before the show, we were talking about kids understanding the idea of the number of the mole. And it's just such an extraordinary number. It's almost unfathomable. It's a number that I can't conceivably count.
Yeah.
And, nobody has ever counted to a mole. So how do we know it's there is one of the questions that you get. How do we know how many particles there are inside here? Now, I think that's the only time that it's really valuable to refer back to how they came about the definition of the mole as 1/12 of 1/12. Why is there a link to carbon in the first place? Why do I describe it as 1 proton equals 1/12 of a carbon-12 atom? That's very wordy.
Yes.
I tend to stay away from it as far as possible. It's one of the most cryptic, sort of confusing and convoluted definitions there is. So my best advice to teachers is to stay as far away from that definition as possible, unless you're going to spend some time unpacking it and telling kids, okay, well, this is just a formal definition.
Okay.
It's nothing to be afraid of. Things have to be introduced really softly.
Yeah, I would think so. And is that definition something that they'll ever be assessed on?
I haven't ever seen it directly asked unless it's in a class test.
Okay.
I also see very little value in asking kids to regurgitate it.
That would have been my follow-up question. Which is more important, the definition or the concept?
Sometimes in physics and chemistry, it's really important to know the definition because there's understanding embedded in the sentences.
Okay.
The problem is that the definition of the mole is so full of technical jargon that it's meaningless to most grade 10s. So I would advise that people are not sort of saying, what is the definition of a mole? And can you write it down for a test? Because you're not actually teaching them anything. How can I use a mole is an important question. And, that's really where the gist of this type of teaching should go.
Okay, so they have now figured out that the mole is a big number.
It's a massive number, yes.
What is the next step?
Okay.
What would you do next?
Well, now that you've introduced numbers, you're going to say to them, well, why would I need a mole? What is the purpose? Why am I going to go about calculating these astronomically big numbers? And that's where the analogy came in. I think we discussed it in the grade 11 show. The analogy for handling large numbers. So you introduce these massive numbers and you say, well, those numbers are, frankly, a little bit scary to most of us. So you say, well, I'm going to reduce it down to a number which I can understand, a number which I can deal with.
Yes.
Now, I like to keep these examples out because I can say, well, I've got 6,02 times 10 to the 23 atoms inside here. That's an enormous amount of atoms. And that's a really big number to say. Or I have 1 mole, which simplifies the number down to something which, I can have 1 mole or 2 moles or half a mole. And then all of a sudden, handling large numbers of atoms becomes much, much easier.
Okay.
And the analogy which we used, and, I've got half a dozen cupcakes or muffins staring me in the face, smelling really good. And the minute I say something like, oh, there we go, there's proof and evidence on its way.
You're gonna have to lift the muffins.
Yes.
Okay, there we go. All right, so we've got half a dozen muffins, and without the camera even shining there, people already know what I'm talking about.
Yes.
There's coding in a dozen. People have learnt that 1 dozen equals 12. And if I say half a dozen, immediately people chop it in half and say, oh, okay, there must be 6 of these muffins waiting. The longer you wait, I think there's going to be less of them. But
Okay, what are they using this concept for in grade 10?
They are starting with the beginning parts of stoichiometry.
Okay.
Okay, yet another hugely technical term.
Yes.
I tend not to like it, the word stoichiometry. I tend to call it baking in chemistry.
Okay.
This is why I've got baked goods in here.
That's a lot more friendly.
It's a lot more friendly because, stoichiometry, I don't think I've ever used stoichiometry in a sentence which was outside a science classroom. In fact, kids come in and sort of do a double take. You write down stoichiometry on the word and the spelling is,
Yes, it's not like quantitative.
That's the thing. Chemists are all full of really weird jargon and strange words. So stoichiometry is a scary word. Educators really need to be aware of frightening kids with new words. Because a new word means a new concept, and this, especially if I don't understand the word, the immediate connection in the child's mind is, what hope do I have of understanding a concept if I don't understand the word itself?
Yes.
So I sort of tend to sort of candy coat some of the more difficult words before I introduce them directly.
Okay.
Mm-hmm.
Okay, so you're introducing stoichiometry now.
Sure. Okay, so the measurement of chemicals. And the reason for measuring chemicals, a lot of kids sort of say, well, why should I measure chemicals? I'm not going to spend my afternoon measuring out 27 grams of aluminium. What for? Is the obvious question that comes up in class. Why would I do such a thing? Well, it comes down to why kids want to do chemistry in the first place. I want to make something. I would like to turn this chemical into that chemical. I would like to be Professor X and make, do something.
Yeah.
And I'd like to make a new chemical. How would I go about doing that? And one of the steps is using the symbolic representation of using balanced chemical equations.
Okay.
So now that we've balanced chemical equations, we've kept our teacher happy, but why are we doing them? What for? Why would I need to balance chemical equations?
Are you balancing chemical equations in grade 10?
Yeah, and some of us have been introducing them since grade 9.
Okay.
That's part of the section which is representing chemical change. So now you've balanced these chemical equations, but nobody's told you why you're doing this. So you're saying, okay, well, I'm balancing an equation in chemistry. Why? And that for me is the starting point. I like to do representing chemical change and then do quantitative because they tie together very well.
Okay.
So my major thing is in tying the two together is where I represent chemical change as the cooking recipe. Now, there's not enough time in the show, but if you start to mix together ingredients and start to bake them, that's our chemical reaction.
Now, with that baking analogy, and I said this the last show as well,
Sure.
the problem is that you're measuring by grams and by volume. You're measuring by weight and by volume. Are they able to make that switch from there to number of moles?
Well, I would argue that is a strength, because that's the same way that chemists are measuring things out. They're putting things on mass balances. They're measuring out milliliters of certain chemicals and mixing them together. So I really think there's a very strong tie there, because chemists are measuring by mass, the same way that you would measure out by mass in certain recipes.
So could you then argue that 250 grams of flour has a certain number of moles attached to it, and when it's mixed with 150 grams of sugar, it has a different number of moles, or maybe the same number of moles, and they bond together forming...
Absolutely, you could do this. And if you've got really, really good science students and they really want a bit of a challenge, you could ask them to calculate the moles of glucose or starch in a cup of flour, because it's majority starch, which is just lots of glucose.
Okay.
So you could really extend them and say, okay, well, now you're going to go home and do some calculations on the food you're eating. And that's a really great way of making moles real for them, saying, how many moles are you eating today?
How difficult is it to do those kinds of calculations?
If you've got a really sort of switched on interested student, I mean, that's obviously the most important part. Not too difficult at all. As long as you've got a formula to work from in terms of a chemical representation for glucose, C6H12O6, especially if they're doing life sciences, that's a really nice way to tie the two together. You could say, well, how many moles of glucose did you eat at lunch today? Come into the science lab and put your bread on the mass balance and calculate.
Okay.
So I mean that's just really one of the ways that you can make moles real. How many moles of glucose do you need a day to keep alive? How many moles of water did you consume this morning? So I mean it's just a different way of thinking about quantities. When you say how many. And this is one of my points that's going to come up later, is really to use physical language. Please, when you get too involved in formulae, it becomes very abstract. It becomes untangible. You can't imagine, what can I do with 1 mole? Oh, I can pick it up. I can put it into my reaction. We can mix the two together. We can get 2 moles of something else out. And I like to speak with my hands a lot. Especially when you're talking about chemical formulae. So I'm putting something in, and then I'm taking something out.
We do the same in maths when we're teaching concepts for the first time. Instead
Absolutely.
of saying we're adding this and this,
Sure.
or we're plussing, which plus is a new term, you say, well, let's put them together and
Sure.
see what happens. So,
And you establish the idea of what plus really is for them.
yes. Okay. Now, tell us what's next.
Okay, well, now that we've established why we're going to be doing moles and a couple of the easy ways to introduce moles, I thought I might show you some of the interesting hooks that you might use. One of the interesting things that I like to do is, an electrolysis of water and then the water-forming reaction, because it's probably the first reaction that people were taught to write out. It's how do I make water and how can I pull water apart? It's the first formula or chemical formula that I knew.
Now, you warned us about this experiment in the last show and what a big noise it makes.
Well, I'm trying to limit the noise today.
Thank you.
Okay, and I've tried to make it with as simple apparatus as possible. I just need to give a little bit of a safety warning.
Yes.
Please, if you are going to try this, we are going to be making a stoichiometric, so there's the word again, a stoichiometric mixture of hydrogen and oxygen. Now that mixture is highly explosive. It's so explosive it sends rockets into space. So, and you've got to be very, very careful about generating this mixture.
So that means that you're splitting the water into
Absolutely.
1 hydrogen and 2 oxygen.
Correct, and that introduces the idea of ratios of chemicals to each other.
Okay.
So even if you start taking a look at the electrolysis here, maybe I can even bring it around and we can focus on it with the camera. Let me just get the moles of the other chemicals out of the way. I'm not sure how close Dylan can get there, but let's see what we can do with this. So I've got myself a very strange-looking console jar, and I've done this on purpose. They're very nice, sturdy jars, but inside I've got 2 electrodes. And maybe I can unplug this and just bring it a little bit closer for Dylan's purposes. So I've got these 2 electrodes over here. These 2 lead electrodes are going to make hydrogen and oxygen. The really beautiful thing about this is when you do the electrolysis, you can actually see that there's twice as many bubbles on the one electrode as there are on the other electrode. So it's really nice that you can see that there's double the amount of substance on the one electrode than the other electrode. Now, if you're very careful, you can make apparatus and collect them separately. Unfortunately, those apparatus they tend to break very easily, and they're very, very costly.
Okay.
But it's a very visual way of seeing, okay, no, there's 2 parts of one gas and 1 part of the other gas.
Okay.
And immediately inside, there's students going, okay, you're making an explosive, and there's 2 parts of the one and 1 part of the other, and it comes from water. Now, I don't like to tell them any more than that, because immediately they start to put together the puzzle in their mind, and they start to discuss with each other. They're not going to get purely fascinated by me talking or lecturing.
Yes.
I want them to wonder about it. I want them to puzzle about it, see the bang, and go, okay, how do I make that explosion? And hopefully that's what we're going to do today.
Okay.
So let's plug this in. And
what are you plugging it into?
Okay, I'm plugging this into a power pack. Anything that supplies 10, 12 volts is fine.
Okay.
A lead acid battery would work fine as well. Now, inside here, I've got a mixture of very, very diluted sulfuric acid and water. That is it. If you want to keep this experiment for physical and chemical change, it's also really nice for teaching exothermic and endothermic reactions.
Okay.
Okay, so let's see if we can get this thing working. So, there we go. Right, so we've got some bubbles coming over here. Right, really, really nice. I'm creating twice as many bubbles on the one side as I am on the other side. I can see that my co-presenters run away from me.
Yeah, on the other
Okay.
side through.
All right, so these really nice long lighters are very nice if you're lighting something explosive. Please make sure that if you are delivering this by a tube, that the end of the tube is underneath the water, because the tube is still filled with the explosive mixture. So you don't want the explosion running back up the tube into the apparatus and exploding glass everywhere. So these bubbles, and there's a little bit of sunlight liquid inside here just to make the bubbles stay where they are. These bubbles have got a perfect ratio of 2 parts hydrogen, 1 part oxygen. And when they combine, they go back to water and release a lot of energy. So let's see. Okay. So you can see that they're starting to go. We can make it even more explosive. And the longer you leave this going, the more explosive they get. So there we go. Right, so you can see that you've got it.
Do it again.
It's always a winner with the kids. I think we've lost our ignition source there. There we go. Right, I think my co-presenter's
Okay, I'm back.
going to run out of the studio if we carry on doing that. But it's particularly nice for them to see that we've got these perfect ratios making something that they can believe. And there's obvious questions on, if we're making water, where are the clouds? Which is quite nice. That leads into a good discussion of, the nature of the things that we're making. So if you bake...
That's a really good point.
Well, absolutely. So if you bake a cake, you've got a solid cake at the end of this. If we're
Yes.
making water, where is the water? So that's a really nice discussion to have with them. So
Is that something they pick up on their own?
well, they say, we can make water. It's one of the weirdest concepts in many learners' mind. I can actually make water. Because up until then, they've said, okay, well, water is something that flows in a river, goes down into a dam, and comes out of my tap.
Yes.
It's not a chemical. They haven't treated it as a chemical. It's something which I drink to quench my thirst. But introducing the idea that water is a real chemical that you can break up into 2 parts hydrogen, 1 part oxygen, and remake is something completely foreign to them.
It is quite a mind-blowing.
And if you really want to challenge them later on, especially when you do the volume calculations, you can challenge them to calculate how much water did I actually make in that explosion. We could actually measure it. You could filter that gas into a measuring cylinder. You can explode a tiny amount, please not in the measuring cylinder, okay, unless it's plastic or something like that. And you can say, well, how much water do I expect? And you challenge them to that. Why can't I see the water? Let them go home, think about it, discuss it, Google it, chat with friends, and come back and give you an answer.
I'm sure you could find a YouTube clip of this thing happening.
absolutely. Very often I've
Yeah.
seen YouTube clips, they just call it HHO gas, which is, H2O gas. So
Okay.
2 parts hydrogen, 1 part oxygen. If you mix them in the perfect ratio, they're very explosive. So nice cheap demonstration and nice way of making a bang. But please be very, very careful. Remember that this tube is still filled up with the explosive gas, and obviously you don't want the explosion traveling back into your glass jar.
No.
So that's something that has been learned the hard way before.
By yourself?
Yeah, absolutely. Okay, before I took all the safety precautions, but just make sure that it's completely submersed.
Okay.
Mm-hmm.
Okay, so when do you move on to calculations?
I try introduce them sort of in bits and pieces. I don't like to give them a massive worksheet to work through. That's one of my last steps. I find that these calculations are consolidation of a concept, not the introduction. So now we've introduced the concept. I'd like to sort of do it bit by bit.
Okay.
When I've introduced these as 1 mole, and I say, well, how do I figure out how many particles are really inside there? And then all of a sudden, very often in the class they'll say, but why 27 grams? And they start to ask questions like that, and that allows you to introduce one equation at a time. So that's where the mass equation comes in. So how do I get mass introduced to be 1 mole? So I tend to follow a slightly more organic way of doing things. I don't say, well, here's your 3 equations. This is how you calculate moles. Because as I said at the beginning, that's really difficult to fathom. They do start to ask, why have you written the masses on the outside?
Yes.
And this is where we can introduce concepts like molecular mass, which is the Mr. in our formulas over here. So in bits and pieces.
Yeah.
It just makes it bite-sized and much easier to digest.
Would it make sense to have I know you said in the beginning, if you put these formulae up on the board, it freaks them out.
Yes.
But if you had them up on the side wall with what each symbol meant or variable meant.
It very much does help. And one at a time and separate from the others.
Okay.
Because I find that just having N, N, and N, it very much clouds the issue. I like to have them next to the appropriate calculation. Okay, Avogadro's number is this, and this will go with this equation where it says the number of moles is equal to number of particles over Avogadro's number. So have it next to the appropriate approach to it. Say, when I've got number of particles, this is the equation to use.
Yes.
When I've got a mass, look, here's an equation with mass inside. When I've got a volume of gas, here is a volume of gas calculation. But having them next to each other tends to be a little bit confusing.
Okay.
What I have seen done successfully before is there's a bit of a mind map on how to get to and from moles. And I think maybe it's worthwhile just explaining what to do there.
Okay. Well, while we get there,
Sure.
we've spoken a lot in previous webinars about the Johnston's triangle.
Yes.
And the symbolic and the macro and the micro. Which parts would be symbolic, which macro, which micro in this case? And would you explicitly say, right now we're talking about the macro?
I think it's very important. I very often start with the macro because that's the world that the
and
kids
the
are born
macro
into.
is what you can see.
Absolutely. This is what I can measure.
Okay.
This is what I can measure with a cup or a spring balance or a measuring cylinder. Because this is how the kids see the world. It's what I can touch. It's what I can sense. It's what I can pick up. Now, linking this to the microscopic is where the numbers come in.
Okay.
Saying, okay, well, I've got 1 mole here. I measure it out on a mass balance. This is my macroscopic measurement. Now, what's going on down at a microscopic level? How can I fit this many atoms? And then you go microscopic with it. And explain to them microscopically, how many atoms is that? Start to get a concept for the numbers. This is where we go into the microscopic.
Okay.
Now, that does link up with the symbolic very much.
Yes, it almost feels like it's kind of more symbolic than it is microscopic.
There is a huge amount of overlap. Now, the only reason to introduce a microscopic is to tell them that atoms are individual things that can be counted at that level.
Okay.
So I say to them, here are a number of atoms. They are separate, discrete items. They are a thing which I can count out the same way that I would with pocket change or grains of rice.
Mm.
And then to represent them symbolically using chemical equations or equations representing moles.
Okay.
And that's where it's very heavy on the symbolism, but jumping straight to the symbolism is very abstract.
Yes. Okay, I interrupted you. You were
No,
on your
no.
way to something.
Oh, okay. Well, just a couple of things. One of the things that does help, and I've seen a lot of teachers do this, is I think they call it a cloud diagram, but I think it's just a fancy way of mind mapping different ways to calculate the mole.
Okay.
Now, because it works quite well, a lot of teachers jump straight into it. So if you have, the mole as a number here, so this is my number of moles.
Yes.
There's various ways of counting out or measuring a mole in various quantities. I can use mass, or I can use volume, or I can use the number of particles. Now, these are macroscopic concepts. Mass, number of particles is closer to microscopic, and volume is very much macroscopic. It's, it's something I can measure in a measuring cylinder, or even, a balloon could measure volume. Gas syringes. But how to convert to and from the mole. Now, realizing that a mole is usually a fraction of a number introduces the idea of mass, multiplication, and division.
Okay.
So now, if I had the number of particles, if I was microscopic and I could count out atoms, how would I find...
had billions of years in your lifetime to count them out.
Absolutely. Yes. So if I knew the number by some magic or tricks, if I knew the number, how would I find out what fraction of a mole I had? Now, remember that mole is a fraction of a number, so to make this into a fraction, I would divide.
Yes.
So I would have to divide that by something to get there. And in this case, I divide by Avogadro's number.
Okay.
Now, in all of the cases where I go from the macroscopic to the number of moles, I'm going to be dividing to emphasize that it is a fraction of a number. So the way to do that from mass is I say, well, how much mass would I need for 1 mole? So then in that case, I would divide by the mass of 1 mole of that substance, which is the relative molecular mass.
Okay.
And in the same way, from the volume of a gas, I would divide by the standard molar volume of a gas, which is 22.4.
Okay.
Now, this is very process-driven, so I don't like to start with this.
Yes.
So there are ways of converting all of these macroscopics into fractions of a mole. And it makes it very easy for kids to say, okay, well, there is just basically one thought process. If I want to reverse all of these and get back to my physical ways of measuring things, either number of particles, mass, or volume, I'd have to multiply to get back out.
Yeah.
Now, I'm not mad about this as a beginning. It's a nice way to summarize the various ways, and it's a nice way to collect all the data onto one. But I've seen this stuck up on the first slide in a lesson, and it's not the correct way to start.
I thought just correct that multiplication
there. Apologies there. This is what happens when you talk and write at the same time.
Yeah, Avogadro's number there, yeah.
Thank you.
Shall we take a look at your 5-step summary or
Absolutely.
5-point teaching strategy?
Absolutely.
Okay.
It's fairly basic. It starts from foundation and works up to a grade 11 level.
Yeah.
Okay.
First one says, find out why measurement is important.
Okay. Well, I like to ask some questions. Why is it important to take a look? The reason I've got some blueberry muffins inside here is I asked them to put themselves in a position. So I say to them, how would I go about making 6 muffins? And they say, okay, well, I know how many I have to make. How do I go about this? And they say, okay, well, there's a recipe. Okay, well, what is a recipe? And okay, it's a list of instructions.
Yes.
But I say it's more than just a list of instructions. It tells me specific amounts that I need to put in to make a product. And they say, okay. And then I say, well, if you have to make 6 of these, how many do I have to put in? If I have to make 12 of them, how many do I have to put in? Oh, okay. Now there's a need to know how much you're putting into a chemical reaction. So what is the recipe to make water? What is the recipe to make a particular chemical?
And I suppose all of those questions link to ratio.
Absolutely. And it links up very, very strongly with representing chemical change. And you bring back in the balanced chemical equations. And you're saying, well, there's a ratio of chemicals which go into these. But, and this is the real big but, and this is something I forgot to do while we were exploding water, is if you go back to representing chemical change and chemical formulae, the one thing that I ask them, and this is where the physical language comes in. If I write down something like, I take 2 parts hydrogen, and I take 1 part oxygen, and we balance them into water. So we've got H2O. Let's just get our actual H2O out of the way there. So let's just balance this chemical equation. And they say, okay, well, I've got to balance it because atoms in need to equal atoms out. This is what my teachers taught me. And I say, well, how would you go about this? How would I get 2 parts of hydrogen? How would I get 1 part of oxygen? And usually they're stumped then. Do I say to them, okay, well, you're going to go and find me 2 molecules of hydrogen and 1 molecule of oxygen, sorry. And they say, well, that sounds reasonable. And you say, well, how are you going to find 2 molecules of oxygen? And that brings in the microscopic aspect. And they say, oh, no, we can't do that. We can't go and get 2 molecules of hydrogen and 1 molecule of oxygen.
And their reason would be because they can't count
absolutely,
the atoms.
They're too tiny. So how do we deal with them? And then I say, well, okay, well, if I took 2 lumps of this, I don't even call it moles at that stage.
Yeah.
I say, well, if I took 2 parts or lumps of hydrogen and 1 lump of oxygen, I could still combine to get the same ratio. So in the same way that I can deal with a blueberry muffin recipe, I can scale things up.
Okay.
I don't need to go with 2 molecules. I could go with 4 molecules or 8 molecules and start to scale it up, and eventually I've got an amount which I can actually measure out.
So you're introducing concepts slowly.
Absolutely.
And in a friendly way. You're building from the familiar and going towards more abstract.
Absolutely. The equations are the most abstract part of this, and I like to stay away from them as long as possible.
Okay. That being said, though, you've just put one down here and said
Oh, no, I mean the mole calculations.
Okay.
But that said, chemical equations are a daunting thing. There's a huge amount of sense to me. This means that I've got 2 molecules of hydrogen covalently bonded to each other, added to... There's a huge amount of information coded into a chemical equation, which people take for granted. And the symbolism there is really intense. You could write a page on what this equation actually means. It represents... conservation of mass. It tells me that these 2 hydrogens are joined together, they're diatomic. This tells me that they've got a single valency with oxygen.
Yes.
And like you say, the fact that I've just written one down should be done with caution.
Okay. Step 2, or point 2, introduce Avogadro's number mole concept.
Okay. Now, most of what we've been doing this show is a slow introduction to that. Now, just simply writing that number on the board and saying Avogadro's number is 6,02 times 10 to the 23 is not the way to go about it. Introduce it as a way to measure things. It's just a number. It really is just a number. People say, no, it's a thing in chemistry. No, you could talk about a mole of anything and encourage the kids to use it in their own language. I could have a mole of marbles. I wish I had a mole of money. Don't we all? But that would mean that it would, be unfathomably rich. But, this is the thing. Tell them to use the mole in sentences describing something other than chemicals, because it is just a number which can be used anywhere else. I don't think there is a mole of too many things. But it is something specific to chemistry, and... just sort of disarm the concept a little bit. Say, yes, here's Avogadro. He managed to figure out this particular number. And it was named after him because he figured out... And it was actually after combining volumes of hydrogen and oxygen.
Okay.
It's nice to have a little bit of a history. And then all of a sudden a number becomes less important. And it just becomes, I've got a mole of something.
Yeah.
It just becomes much more commonplace.
Could you liken it to no, you can't really liken it to a ton, because a ton is a measurement.
Sure, a ton is a measurement specifically of... That's why I like to use the example of a baker's dozen of 12.
Yes.
Because a dozen is just... You can have a dozen of anything. You can have a dozen hens, you can have a dozen eggs, you can have a dozen rolls or whatever you might... Or you can have a half or a multiple of 2, which is quite nice because they're quite used to using that as a multiple, as a number. And you're just saying, well, this is just a different number. Instead of 12, it's this number.
Yeah.
And be careful with the number as well, because a lot of them are struggling to put it into their calculators properly as well. So spend a little bit of time making sure that scientific notation on the calculator is a skill that they know.
Yeah, because it's not something that's practiced very often in maths. I think grade 8, grade 9 is the last time they do it.
Well, that's the thing. And they're not very comfortable with it, and it even comes back to harm them in other parts of science. If you're not comfy putting in scientific notation, it's going to harm you.
Okay. Point 3, the number of moles particles in various substances by mass or volume.
Okay, now that's just introducing the most basic ways of calculating moles. So that's where you can, now that you've introduced the concept and you spend 2 or 3 lessons on why should we measure things, I mean, it's an extraordinary number. Now that we've introduced how big the number is, how do we go about getting it? What are the chemical means of doing it? Now, again, I would even still avoid walking into the classroom and saying, this is how you calculate mass into moles. This is not the approach. Very often, since I've used these mole examples, again, I ask them to say, okay, well, I've got aluminium with 27 grams written on the outside. Have a look on the periodic table and see if you can see why I wrote that 27 grams. And they'll look and they'll start sort of wondering, okay, he got that 27 grams. And I don't even tell them when they've got it right, because I ask them then to say, is the reason that you found the same reason that I wrote 32.1 grams on sulfur?
That's a really, really good technique.
And then I ask them, okay, well, I've got something else here. This has got 3 different types of atoms inside. Now, here's a challenge. Go and figure out why I've written 100 grams on here. Now, they'll say, okay, well, I saw the mass number on sulfur and it said 32.1.
Okay.
And I saw the mass number on aluminium and it said 27.
Yes, and this one is calcium something.
So there's calcium carbonate inside there.
Thank you.
Is it possible that if I add these up, that I'll get 100 grams? And the fact that they figured it out and they're saying, there's something here. There's a way to find out why he's written those masses on there. And then you're saying, okay, well, what you've just figured out is how to get relative molar mass. And then all of a sudden having a little mister at the bottom of your equation is really not a threatening thing. You're saying, okay, well, how many misters do I actually have inside this particular jar? If I had, for instance, 54 grams, then how many would I have inside here? Well, if 27 was 1 mole, then 54 is naturally doubling that. Then all of a sudden you've said, okay, well, now here's just a formal way of putting it all together.
Yes.
And then the equation is almost an afterthought. They've actually figured out the algorithm for themselves.
Yes.
And then you're just saying, well, all I've got to do is I've got to find out how many 27s I've got in here, how many 32.1s I've got in here. And then naturally from a lot of the maths bit they've been doing in the introductory grades, they're saying, well, how many of this do I have inside this? Instinctively, usually they're dividing inside their minds anyway.
That's fantastic.
Then we don't need shortcuts. We don't need cloud diagrams. We don't need complicated equations on the board.
Yeah.
And, that's when you can introduce the equation. That's when it becomes safe. Because they've actually figured out the reason they're doing it. And they're saying, oh, I've got that. Sorry, we're going to talk about volume as well.
Yes.
If we've got a little bit of time.
Of course.
Okay, now, volume is another way that they like to measure things. Now, volume something you've got to be a little bit careful of, because you can measure volume of a solid. And if you're using the baking example, they're saying, it's like having a cup of sulfur. Now, the volume that they need to use to calculate things in chemistry is specific to gases. And that's tying back to Avogadro's concept of 22.4 decimeters cubed per mole.
Yes.
Now, that is a discussion lesson all of itself. How is it possible that no matter what gas you've got inside a particular container, it still has the same volume, no matter what substance it is? So if I've got 1 mole of hydrogen, it's 22.4 decimeters cubed. 1 mole of oxygen, which is 8 times more heavy, but it still occupies exactly the same volume. And that's a really, really good way of testing the kids' microscopic understanding of gases.
Okay.
So it's a really nice sort of starting point to a lesson. You can hold up to them 2 containers or 2 glasses even, and say, I have the same number of molecules inside each one of these containers. And that's a really, really good starting point, because it undresses what actually is a gas.
Yeah.
And it's an entirely separate talking point if we've got a little bit of time.
Well, We were talking about hooks later, and I think
Absolutely.
that just shows that your hook doesn't have to be some demonstration that you do. It could be
it can be a question.
A question, yes.
You can say, well, I've got 1 mole of hydrogen, the lightest gas, and I've got 1 mole of oxygen. You could even have 1 mole of xenon, which is intensely heavy, or even krypton gas. And it would still occupy exactly the same volume. It doesn't matter how big and fat and heavy these atoms are.
Yeah.
Still the same volume. And that's a really pivotal way of sort of saying, okay, well, how is that possible?
Yeah. We don't actually have much time left.
Okay.
So the next point says link them all to conservation of mass, stoichiometry.
Okay, now that's a very good place to do demonstrations. Like I've got 2 parts hydrogen, 1 part oxygen to make water.
Okay.
That links up with the symbolism of the equation very, very nicely. But that question that we asked a little bit earlier, if I'm making water, where is it?
Yes.
It's really nice to ask them, if I've got a certain volume of this and a certain volume of this, what mass can I expect of water? And because it's an intriguing question, they're sort of saying, okay, well, I need to figure out the details to give you an answer. And a lot of them will be sort of inspired to be able to do that. Now, the mass of water that you calculate from here is in the range of milligrams. It's so little that it's actually a gas.
Okay.
And that's the answer that you hope they get to. There's so little water, it's almost impossible to see.
Okay.
If you want to sort of say, well, I can show you a lot of water being formed. If you've got access to video, you can actually show them one of the space shuttles going off. There's an enormous amount of water being emitted from those rocket engines. So you can show them there is real water. These things are making real clouds, and it actually rains around the launch site.
Yes.
So, I mean, you can make it tangible. You say, well, if I scale up this reaction, this is what we can do.
I just thought it was always bad weather on launch days.
There's always clouds. Well, I mean, one of the things that you can actually do on NASA's website, you can look at the design of the space shuttle's fuel tanks, and you can ask them, why is the fuel tank for the oxygen so much smaller than the one for hydrogen? And you can actually see they're in a roughly 2-to-1 ratio, which is quite nice. You're saying, well, H2O.
Yes.
And that's sort of, oh, wow, it's real. People can mix things together and explode things out into space. It sort of reinforces the idea of why scientists need to measure things.
So, your last point says variety of practice examples and analogies.
Okay, as many examples as possible. They can't just stretch to a box of aluminium and sulfur and calcium carbonate and all sorts of other things. You've got to expose them to moles of ions. Specifically, that was one of the practice examples that comes up and hurts a lot of people. For instance, if I was to ask you, let's say we were talking about the example of glucose.
Yes.
The starch that people were eating at lunchtime. If I had a formula of C6H12O6, so I mean that's the basic empirical formula for most of white bread. So if I took this and we found the relative formula mass for this, we could calculate the moles of glucose that you ate for lunch. But now what if I asked them, how many atoms did you eat of oxygen? All of a sudden you're saying, oh, okay, well, wait a minute. I thought I was talking about glucose. It introduced an extra level of complexity.
Yes.
They've now got to realize that in the symbolism, they've calculated the moles of units here. This entire thing as 1 unit. But within that, there's 6 times as many carbon atoms. There are 12 times as many hydrogen atoms, 6 times as many oxygen atoms. So start to go, okay, well, I can calculate relative formula mass, but I can go further than that. I can say, well, how many oxygen atoms did you eat in your bread today? And it sort of floors them. And I say, okay, well, how would I get there? And they start to develop problem-solving strategies that way.
Is that the type of level 4 question that they would get in an exam?
Well, this is the thing. It's not in any textbook. You probably didn't cover it in class. And it does require a true original thought. That level 3, level 4 questions where they've got to apply and invent new strategies. Now, if they're not used to inventing new strategies, the biggest complaint I find from other educators is these kids can't think for themselves. And we're partly to blame for that.
Yeah, I think we are, because we encourage conformity, don't we?
Well, absolutely. We're saying if you put the numbers into this calculation, you'll get an answer. And do that, and it's safe. But that limits kids. That means that they're not getting that 10% of level 4 questions.
So I have a question now which
Sure.
is slightly off topic, but kind of on topic as well.
I like those.
Do you think that if we taught a class only at that level 4 thinking, we didn't ever go with this is how you use a formula, it's always they develop the concepts, things like that. Do you think that they would perform well in an exam?
Partially. I think teaching at multiple levels is still necessary because you've got different types of learners inside the classroom as well. There are those who naturally critically analyze things and have original thought. If you did get them all used to it, perhaps they would do a little bit better. But I think there's different levels of thought inside any person. If you're a critical thinker or not, even critical thinkers have got functional parts of their brain, I think, that are just, okay, there's a routine calculation. Let me get that out of the way quickly and get onto the critical thought. I think each learner is made up of, multiple layers. They do have parts that are dedicated to, okay, well, here's something I can get out of the way, and I've got a mechanism for that. Let me get onto the part that's interesting and engaging. So to answer your question, I think while it might be a challenge, it might be worthwhile. I still think it's necessary to have some sort of routine as a mixture with that, as a support to that.
Yeah.
I think it might be quite difficult to teach only critically.
Yeah.
That would be an immense challenge. I'm not sure how I would approach that, to be honest.
No, I don't know either.
But, it's something to strive for. At the moment, I would say that we commit very little bit of very little amount of class time to critical analysis. It's mostly to rote learning and repetitive exercise, which destroys that sort of thinking.
It does, but at the same time, there's so much to do, especially in physical science. There's so much to get through, and there's that assessment at the end of the year.
The syllabus is full, and people are pressed for time. But a lot of these critical thinking, sort of discovery of, a molecular mass for themselves. I found this particular one where they've got to look on the periodic table. This saves me time because I don't have to spend 5 lessons trying to hammer it into them and saying, this is how you do it, this is how you do it. They go, I understand that, don't worry, let's move on. So sometimes these critical exercises really can actually save you time. But
it makes sense that it would.
That's the thing. If you can find a way that makes a concept stick more fully, it means that you're going to save yourself time on just endless exercises.
Yeah.
Other sections where that sort of thinking, that sort of teaching really saves a lot of time, electricity, electrical circuits. And that's another big one in grade 10, which is a bugbear. It's a problem for a lot of learners, a lot of teachers. How do I teach this? Do a lot more discovery, and you're going to save yourself a lot more time.
Well, thank you very much for coming. Remember that if you have interesting ideas, especially the kinds of ones where you discover things critically, I hope I used the right words there.
Yeah, well, absolutely.
Oh, good. If you have those kinds of ideas, please send them through. Just remember to put the secret code in the subject line, and you can email them through to competitions@digitalclassroom.co.za. You can also find more details at the website digitalclassroom.co.za/webinars. And we look forward to having you again next week, where we'll be discussing grade 11 physical science. Yes. Thank you, Dylan, for the background.
Yeah, absolutely.
Thank you, Phil.
Oh, well, I'm glad I didn't blow up the studio.
I'm really glad you didn't either.
There's always time.
I like my job. Goodbye.
Bye-bye.
Using how to